Hello, everyone. Um, I think we will get started. Aren't you ready?
Yeah.
Cool. Yeah, let's get started. Thank you everyone for joining us. Yeah, I'll put up the list of papers that we're talking about today, which Aaron had posted. So we will be starting out by having eMozilla from, I guess I don't know if that's how you say it, but eMozilla from News Research to present Hermes 3. So I will add him as a speaker. Let's see here. Okay, let's see here. So, as usual, I guess I don't know if there's like difficulties or something. Let's see here. Why? It says that I've invited him, so I think Mozilla has to accept. At least it's better than last time where I wouldn't see the person in the space to begin with.
Yeah. Has he requested to be a speaker?
No, not yet. I sent him a request. Okay, there you go. Now it says he's a speaker.
Hey there.
Hello. Yeah, we can hear you.
Awesome.
Cool. Yeah. I guess feel free to get started. We'll share the Hermes 3 paper, the tweet in the space, so people can or have access to the link as well. But yeah, go ahead and we'd love to hear more about Hermes 3.
All right. Hi there, everyone. My name is eMozilla. You did guess correct. One of the co-founders of News Research, along with some other people you might know, Technium, Mephisto, and Shivani. So the four of us together were the original co-founders, but we've grown a lot. And our most recent release is the Hermes 3 model. The Hermes models were kind of what got us a lot of attention at first. And one of the things about Hermes that made Hermes special, especially in the beginning, is that we were really quite early to the synthetic data sort of, thought process or paradigm. Fast rewind, I would say, several years ago, there was sort of this question, and I still, you still see it maybe in areas outside of LLMs. Maybe when you describe what it is we do to people on the street, that an AI could ever make some training data that would be able to help train another model. There's this like intuition of mode of that somehow there's this like nugget of realism in human written text, and that once an AI touches it, anything that comes out of an AI is necessarily like downfield. But I think we've broadly seen over the last several years, and the original Hermes was an example of it, and then later on with things like Lima and now Phi and other papers that show that synthetic, and I know NVIDIA today just released this distillation. They've been working on this distillation stuff. They really show that you can have teacher models that both create synthetic data and that the models trained from that synthetic data can improve. So nearly all of the data inside of Hermes 3 was synthetically generated. We used different models, the frontier models, llama models, these different ones at different stages for different tasks. But nearly all of the data itself is synthetically generated, which sort of was different from the Hermes 2 series, which was a mix of synthetic and sort of what we would call high quality chat conversation data, where you were just taking highly rated chat conversations from other LLMs and training on that. we took this really a step further, where for every data sample, we took it through a synthetic pipeline that that augmented it, that would judge its quality, make changes to it, regenerate it, and so forth. And this was pioneered, it originally pioneered with the eval instruct method, but we've since done a lot more with our pipeline. But that sort of is the genesis of the idea, is that you're really, even for like real world data, quote unquote, like conversations, you are synthetically augmenting it, and then out of that you get a better model. So Hermes 3 was designed from the start to be this sort of neutrally aligned. So it's important to us that, and we state sort of in the preface of the paper and like the introduction, that a lot of chat assistant models can be sort of moralizing or have refusals and stuff. And really, at the base model layer, we just don't think that like this is the appropriate place for lobotomization or whatever you want to call it. That the mind should be free to think, and that it is the things we do with our thoughts that largely dictate what we decide is bad, and that there should be no thought crime, I'd say. So we've put a high emphasis on making sure that the system prompt is the ultimate constitution to Hermes 3. So much of the training data is really explicitly trying to make the system prompt be the thing that matters, and how it answers. And this is important because it allows the model to sort of place itself within different frames of thought. If you think about like the default assistant that you get from ChatGPT, Claude, Llama 3 Instruct, what you get is this, there's this persona, and it's adopted this worldview of sort of this helpful but paternalistic idea. And that is just sort of like that is the only thing it can be, right? Whereas with Hermes 3, the system prompt tells the model like what sort of world of thought to place itself into. The system prompt does, and this is very powerful because you can get all sorts of behavior that you can't get out of a normal instruct tuned model. But it also makes the model slightly, I wouldn't say more difficult to use, but it requires more control, because you aren't getting the helpful assistant is just one aspect of what Hermes 3 can be. But Hermes 3 can be much more than just the helpful assistant, and that is dictated by the system prompt. And we discovered this on the 405B, some sort of like peculiar generations where if we didn't have a system prompt, the model would like start talking about not knowing where it is and all these other things. And then we did some investigation. We discovered that what had happened was the model actually, in the absence of a system prompt at all, it decided it needed to create a world. It needed to place itself in a world where the absence of the system prompt was the world, right? Like there was nothingness in the world. The world consisted of nothing because the system prompt is everything, but there's no system prompt. So it created this world where like it was role playing as this amnesiac character because it needed to justify a world where this is what a world is with no system prompt. So we kind of had a lot of interesting things that we found along the way, but ultimately, most, as people will tell you, most models come down to the data, and the data is where the secret sauce, you could say, if there is such a thing. And the secret sauce, would be the synthetic mechanisms. But the overarching goal was the idea of making this neutrally aligned model that still instructs tuned. It's not a base model, but isn't just the helpful assistant. So that was what we did on the data side. And on the training side, we did some pretty, I would say it was a standard training regimen, although done pretty rigorously, with hyperparameter sweeps for learning rates and looking at how different epochs are doing. And if you look in the Llama 3.1 paper, they talk a lot about, basically we did a lot of the same things that was done in the Llama 3.1 paper, which is you sort of going beyond just doing a single training, but doing multiple trainings, merging, although we didn't merge with this in the end, do any merging. And one thing that we found actually was that as the model sizes got larger, the need for using DPO, we actually trained the DPO versions, but found that they didn't do much. So we actually stuck with the SFT versions for the 770B and the 405B. And what may be unique in the training process that's different that hasn't been done was that mod one potential other example, which we were not aware of because it wasn't marked as it on Hugging Face. And we actually asked the Hugging Face team beforehand, and they said that this was true, was that this was the first sort of full parameter fine tune of 405B. And that, if there's something interesting in the training, I would say it was what it took to wrestle 405B and really at what it takes to actually train it, which is sort of a whole other beast than what we've dealt with before. A side note, I mentioned this on another space, and I don't think I've been corrected yet, which is usually how things work. I say stuff and then people later correct me. But which is that I'm not aware the 405B. So we know, for example, that I believe we know, quote unquote, that GPT-4 is like around 1 trillion parameters, the big one, and that it's like a Mo, and I believe the same is true for Claude. So as far as I know, it may even be that Llama 31405B is, at least as far as, and especially with tokens, like the deepest, longest trained, biggest dense transformer that has ever been trained. And so it's sort of special that in the open source community, we actually even get access to this. So training 405B was a bit of a challenge. You run into all sorts of things that like PyTorch can't, like when you go to save checkpoints, it'll like run out of CPU memory because it like can't even fit the model in CPU memory. And when it's trying to like save to safe tensors, and you have to do the efficient loading where like you are never materialize the entire model on a single node even. So a single HGX only has 640 gigabytes of VRAM. You, in BF16, 405B, which is actually 410B, if anyone's keeping count at home, is 820 gigabytes of that. So you can't even like, at any stage of your training process, like materialize the tensors all within a single node even. So there's a lot of things that it took to go around and figure out just how exactly that works. Using sample packing, which was key. We used Flash Attention 2's attention mask-free sample packing, which is where you are able to train multiple samples within one sequence, and you can use position. You set the rope positions, you reset them, and then Flash Attention 2, you pass the sequence lengths of all the sequences, and then it doesn't allow cross-contamination. And that was very important because we had a highly heterogeneous set of data that it took, of data lengths within the training set. And so that was really important for the efficiency. And in the end, what we came up with was 3 sets of models, the 8B, the 70B, and the 405B, which from an evaluation perspective are essentially at par with Llama 3.1 Instruct. So they beat us on a couple of things, particularly IF eval, which I have thoughts on IF eval, but IF eval and a few points on like MMOU Pro. We win on some other things like GPQA and Big Bench, MUSR. So broadly speaking, though, it was about a tie with Llama 3.1 Instruct, which ultimately, we were actually very happy with. Llama 3.1 Instruct is an extremely strong model. Meta did a very good job with it. I wouldn't say that would have been true. I wouldn't have said the same thing about the chats that they did for 2 and 1, but 3's Instruct model is very good. And so where we feel Hermes is differentiated is really just that it isn't just the helpful assistant, right? Like it's an Instruct model that's excellent at role playing, function calling. It has a whole bunch of extra features for built-in. It was trained on like billions of tokens of RAG and citations and tool use. So there's a lot of like extra stuff that went into it too. And so that we have like this neutrally aligned, uncensored version of Llama 3.1 Instruct. We were happy with that result. And we've put it out there and had a lot of people seem to really be enjoying it. We were lucky that Lambda Labs, now Lambda API, I believe, you might know them as Lambda Labs, sponsored some of the compute for Hermes 3 and has been offering Hermes 3 405B for free through their chat interface. So we have a couple of, so like anyone can actually go use it. We also have a fun bot in our Discord that is Llama 3 4, that is Hermes 3 405B that people have had a lot of fun interacting with, for free. So we used an FP8 quantization method from a company called Neural Magic to quantize the 405B down to FP8. And you can inference that using BLLM on a single HGX node, all the way up to 128K context. So insofar as you consider a single HGX node accessible to people, we sort of finally do have GPT-4-ish at home. You can run it yourself, and we got there. So yeah, that's Hermes 3, and I guess I might have gone a little bit over time, but happy to take any questions or anything else.
Yeah, that was really interesting. Yeah, thank you for doing that overview. Yeah, if people have questions, they can add it as a reply to the space here. But I had a couple of questions. I think one question, yeah, I guess you mentioned you mostly are using synthetic data, but then, and I guess you're doing SFT on the synthetic data, but then you also do on top of that DPO. So I'm assuming the DPO is just done on like standard like chat conversations and things like this. Is that correct, or is it done also on synthetic data?
It actually had synthetic data as well, particularly for function calling alignment. It helped a lot on the smaller model.
Okay.
So I mean, there was like the binary preference stuff that, you normally see of just good chat, bad chat, good chat, bad chat. But there were some, we did find that we have some synthetic DPO instruction sets that we created that did help the instruct calling in particular, the tool calling in particular for some of the smaller models, or for the smaller model.
Okay. And there's not much improvement on just like instruction following or just general sort of chatting, right?
Yeah, and then on the 70B and the 405B, we did not find that it made much of a material difference in that the SFT had, correctly learned everything we wanted it to learn through the SFT, more or less. It was behaving as we wanted it to. So for the 70B and the 405B, we actually trained the DPO'd versions, but actually stuck with the SFT.
Okay. And what was the size of the data set? I'm not sure if you mentioned that already. The size of your
we do have it in the paper. Let me scroll up and see. It's about 400 million tokens, unique new tokens. Yeah. Trained over either 4 or 3 epochs. So we had some metrics with evals, and we basically would run it and then see where, like for the 70B, we actually took the 3rd epoch, whereas the 4th and for the 8B and the 405B, we took the 4th epoch of training. So
I see. And so you're selecting that based on just metrics in the validation set.
Yeah.
Okay. Cool. Aaron, did you have any questions?
Oh yeah. So Hermes models tend to be like it's very popular among like local Llama people, but 70B and 405B, even after quantization, it's kind of hard to use for in local settings. So I guess it's expected that people are going to use it on like a cloud setting, like possibly like together with somebody like that is going to host it, and people are going to use it.
Yeah, more or less. Although with 70B, certainly people who have MacBook Pros can do a lot. And with 70B, you can, if you have 2 video cards, you can do like Q5 quant on 70Bs, and they're pretty good. You can run it there. I find using Llama CPP Q5 KM is kind of like this. I think that's like the sweet spot of acceptable. That's anything more than that, and you may as well use a smaller model than do quantization at that level. But the Q5KM versions and we have pre-GGUF versions of all the models as well. And for the 70B, if you do the Q5KM, that's around like 20 some gigabytes. So it's still perhaps 30 gigabytes. So it's perhaps still usable. I will tell a slight anecdote. We had a conversation actually with the Meta team, and I actually did bring this up to them and ask them when asked sort of like as an ask from the community sort of that they consider, when selecting model sizes, to think about what class of people can use each of these model sizes, and to make a selection of the model sizes they choose to train, to have that be a factor, not so much as just make it 10 times bigger, but like think about who can use this. And I was happy, and I was interested in the paper where they talk about 405B, and that it was specifically chosen to be able to be run on a single HGX under FP8. That's like as big as you can go. Now, where 70B fits in that, or whether that's a vestige of the fact that they did 170B and 270B, we never did get Llama 2 33B, interestingly enough, and I maybe would have liked to see a Llama 3 33B or something along that line. But yeah, I would say there is kind of a dwarf right now from the 8 to the 70, and we do have things like Mistral 12B that sort of start to fill out that gap between the two. But I would agree there's a calling for like a really good like 20B dense 15 trillion token parameter model. So anyone with a couple $1 million of GPU sitting around, if you guys want to get on that, we'd all appreciate it.
Okay, yeah. Thanks for your answer. That was very informative. By the way, there was a question about the synthetic data pipeline. Did you use any special technique or trick to generate data that favor following the system prompt more closely?
It's not a specific technique. It's really 50 different things, each per domain. And this is really where like the secret really is, and I cannot take any credit for this. This is basically null value tensor, and who also goes by Gifted Gummy Bee, and Technium did this totally out. That's their whole thing. I didn't make any of the data myself. And it really comes down to a meticulous neurosity. This is neurotic about like, okay. I've seen Ryan Tech has this giant flowchart where he's got hundreds of different tasks and like what would make it good at each of these, and like each of these different things has its own py file that is its own synthetic data pipeline to like elicit that behavior. And it really is, there is no magic bullet to make it all good. Or there is a magic bullet and you can scale it up. But if you want to do it as a literally 1 and 2 person team, we're able to meet Llama 3.1 instruct. It really took like just looking at every, thinking about every task, collecting it, hearing what people want to do. And I will offer this one piece of advice for synthetic data, and Tech echoes this a lot, is you actually have to look at the data. He's like, he tells me all the time, he's like amazed about how data sets, he's like, did they look at what was in it? He just go through it with your eyes and really use that piece of you that's special at which humans are great at, which are few shot classifiers, and really get a feel for, is this really what I think I want in it too? And it may not be like the most exciting work, but if you want the best results, it's certainly the path to it.
That makes sense. By the way, another question. Are you guys, what about Gemma 2 27B? Are you guys interested in it?
Yes, so that is I wouldn't say it's not happening at this moment, but we are looking, and most likely probably we will do it soon. Yeah.
Thank you.
I'm also curious if you guys are like, of course there's a lot of talk about Llama 3, Llama potentially being multimodal in the future, having the multimodal variants. Are you guys interested in multimodal models as well? Is that something you guys plan to work on in the future?
I mean, obviously, I would say it's likely the future. So if we want to be in the future, we will have to. I am aware that this is yet one more step of complexity. I mean, it's a whole other level of game, just like the big models are a whole other level of game, particularly because of like the data requirements, right? Everything, the data sourcing becomes even one more magnitude more difficult. We are interested in it. What I'm personally interested more in is what. And now this disclaimer, wild speculation, none of this comes from any source. No one has told me this. This is only me saying what I think. Is that my guess is that Llama 4 will be Chameleon, right? And that Chameleon is the blueprint for what Model 4, Llama 4 will be, which is fused multimodal training, right? Whereas with Llama 3, Llama 3, they train the model and then they do all this extra stuff at the end to like make the multimodal stuff work. But, Meta was in the Chameleon paper, they seem convicted, and the results seem to say that like true fused or early stage multimodal training, is all you need. And that it's interesting because a lot of the complexities in multimodal actually like fall away when you do fused early training, right? Like you just let the model figure it out versus having to like do all this extra patchwork at the end to make the multimodal stuff work. So I'm excited, particularly in whatever sort of emergence we get that arises out of, like a properly fully trained chameleon style dense multimodal early fusion model.
Yeah, definitely. But I think the problem with maybe some of these fused multimodal models is, my understanding is that the data requirements are again quite high for that. Maybe I don't know. Maybe someone can correct me if I'm wrong, but that was my understanding. So, but yeah, I mean, I obviously it's very interesting that it's easy to just have it as one kind of single transformer that you can throw data at and it learns everything. But yeah, we'll see how what happens with Llama, the next Llama model.
Yeah, the current problem with fused model is that you're using decoder transformer in contrast to like a encoded bidirectional attention transformer that is used on like a disjoint type model. So sometimes image recognition type problems, their accuracy is not as good as disjoint models. So yeah, but there have been a few papers that have been propose some countermeasures to it. So yeah, I'm sure Llama 4 is gonna try something like that, I guess. So sorry, another question. So did you look into expanding the context window in the post-training stage, like up to 1 million tokens?
That is a good question. We have not tackled it yet. The Llama, interesting note I will also put in here is that so they did extend, they used a method to do the extension, but they actually don't talk in the paper at all about the actual technical method that they used to do the extension. They just say, we did some iterative context length extension, but they leave out the fact that they actually have a new rope method. It's essentially, so when we originally at News put out the Yarn paper, which was then later incorporated into DeepSeek and then Phi and then DeepSeek and now Llama. It's not Yarn in particular. It's actually more a variant of long Yarn, I would say, is what they did. But they mentioned in the comments of like the transformer code about like doing this grid search to like find the optimal scaling parameters for the rope embeddings to do that. But what's that actually is completely absent from the paper. So I'm not entirely sure why that is, but looking at it, we can infer how it was done. So I think it absolutely can be done. If you read the paper, they start to mention some of the complexities of dealing with these sequences, especially for the larger models, and to do that, you really need a proper, I would say 4D parallelism training setup, right? So you need to be, crucially, you need to be doing something like ring attention. So Megatron's context extension or ring attention, which gives you the ability to actually, calculate the attention in parallel across multiple GPUs, because at those large sequence lengths, that is the entire dominating thing, right? Like the model parameters don't even like matter at that point. Like it's totally dominated by by the attention operation, and so which is not traditionally sharded. And so you need to do that. And to do that, they have their own trainer. There's a couple of good open source, I think, things we'll get there. So there's Torch Titan, which is a new project by the PyTorch team, which is going to have all the new, latest and greatest sort of training tricks that you would need to do that. And there's a branch of Torch Titan now that has ring attention and context parallelism. It already is using, so there's a new thing called FSDP2, which is a new way to do FSDP for training. So to do that, I think we might need a little bit of iteration in the open source space on the tooling to do training. But I would expect there's no reason why we couldn't even, for example, take with what we have now and at least get us to like 256 with not that much compute.
Makes sense.
I had one last question, by the way. Quick question. Like, have you looked at like quantization, like how much the quantization affects the performance of the model? So, like you said, it's deployed at FP8 on these APIs. So, like, have you looked at how much that degrades the performance compared to the full model?
Mm-hmm. I would say you lose, I don't know, like 0.3, 0.4 on your benchmarks. There is a point of like emotional contention on this, where some people will say that the vibes are different on the model, like when it's quantized at FP8, even if like the raw scores aren't that much different. The particular mechanism, we did not do the mechanism of quantization that they did for Llama 3.1. They used this like row parallel where they like are quantizing partial layers and leaving others in BF16. We use, like I mentioned previous, it's part of the VLLM project. It's called LLM Compressor by a company called Neuromagic. And they have their own full FP8 mechanism. And from the when we ran it, like I said, it lost maybe like if you got an 84.6, you get an 84.2 or you know what I mean, kind of deal. So it wasn't like meaningful. But I will say there are people who claim that that BF16 to FP8 loses something. But that's certainly in the nebulous realm of the subjective.
Okay, my last question is, Llama 3 and Llama 3.1, and their multilingual performance is much better than the ones before. We are getting more and more multilingual support state-of-the-art models. And actually, Gemma 2 is even better than Llama 3.1 on this regard. So I guess, I'm sure there are many people who do not speak, whose primary language is not English, who want to enjoy role-playing in a language other than English. Greatly appreciate if, you guys are adding, so appreciate a better performance and multilingual performance of Hermes models. So I guess that's a motivation to try Gemma 2. Well, do you have any multilingual support?
Yeah, and I remember there being some, maybe DeepSeek put it out with, someone has put out, may not be fully rigorous, but like how does multilinguistic abilities in models like improve their lateral thinking? Does learning another language actually make you better at even a single language? And I will say that most of the training data in Hermes 3 is in English because it was synthetic, but it was like it was synthetic with an eye. It was like a human over the shoulder watching all the synthetic data. It's reading it all and doing it, and that was done primarily, not fully, but primarily by native English speakers. So if there's an area we probably have to get better at, it would be that. And you said that there are some people who aren't native English speakers who may enjoy it. I would be remiss if I didn't remind myself that the vast majority of the humans on this planet are not native English speakers, and that we need to think of them as well.
Yeah, absolutely. Thanks for answering all my questions. Do you guys have any other question?
Yeah, I don't see any comments on the space, any new comments. So I think that is all of it. Yeah, but Yeah, thank you, Emozilla, for joining us. This was very interesting, very detailed, and I learned a lot. And yeah, everyone should check out the paper. It's pinned to the space, the Hermes 3 announcement and the link to the paper there, and of course to try out Hermes 3 as well. So yeah, thank you everyone or thank you Emo for speaking about this. Yeah, and I guess we'll move on to the next paper. Which is I just actually next is not really a paper. It's just we just kind of wanted to briefly talk a little bit about 3.5, which was released um, yesterday, and yeah, let me just pin
So-
that. Oh yeah, go ahead, Aaron.
Oh yeah. So 5.3, actually they use 3.8 billion parameters model trained on 3.4 trillion tokens, synthetic data filtered publicly available websites with a focus on very high quality reasoning dense data. So yeah, it's they don't have like a technical report. It's just a Hugging Face page. So yeah, it's just about results. So it performs on par with Llama 3.1 8B on various popular benchmarks. The model belongs to the 5.3 model family and supports 128,000 token context length. So they used SFT, PPO, and DPO to ensure precise instruction adherence and robust safety measures. Actually, I haven't seen many models using both PPO and DPO, so I'm curious what made them to use both. And as for, in particular, multilingual capability is pretty good. So it's actually better than Llama 3.1 8B and worse than Gemma 2 9B. Gemma 2 9B is like by far the best multilingual model under 10 billion models, I guess. So yeah, it's very competitive with state of the art. It performs on par with Llama 3.1 8B on long context benchmarks like Ruler and Lipo QA. So yeah, that's my take. Yeah, I'm glad that there are more and more multilingual powerful models. Tanish, do you have any comments?
Yeah, I mean, they released, of course, the 3.8 billion parameter model, but which is their dense model, the 3.5 mini instruct. But there was also MOE model, and there was also a multimodal model. So there's the MOE model, which is a 42 billion parameter MOE, and that has 6.6 active parameters, and that was trained on 4.9 trillion tokens. So that's more tokens than the 3.8 dense model. So yeah, 4.9 trillion tokens, and again, it's multilingual. 10% of the data set is multilingual there. So that's also pretty interesting. I think this is the first MOE model coming out of the Phi group, if I'm not mistaken. So it's interesting to check that out as well. And then also they have like a multimodal model. They've released multimodal models before, so this is just another sort of multimodal model that they released that is now using the 3.8 billion parameter dense model, which is the Phi 3.5 mini. They're using that as like the base LLM for this multimodal model, so that this has got, it's again like you have the LLM, and then you've got an image encoder, a connector, and projector, and that's connected all to the LLM. And so basically it adds like you have so the total is again like a 4.2 billion parameter model, and it's trained on 500 billion vision and text tokens. And I guess one thing they mentioned is like they're focusing on multi-frame image understanding and reasoning. So like, for example, being able to process videos, and the frame, multiple frames of the videos. So that was something, I guess, with previous models it was difficult to do, and so they focused on that with this new multimodal release as well. So that's, I guess, the other thing I wanted to add. But yeah, I mean, the benchmarks look pretty good. But I guess again, it's I don't know if anyone here has tried the model, if anyone has any sort of vibe check kind of thoughts on the model. I think this is a great release, and again, I think much of the data set is again just based on their previous work on synthetic data combined with more general purpose data. But I guess they don't really go into too much detail about that in the model card or even in the previous papers as well. But yeah, again, importance of synthetic data, I guess. Yeah, I don't know if there's anything else to add. Does anyone have anything that they want to add? Oh, someone was asking, did they mention about the image size or just the image token input size? I am not sure, to be honest. Let's see if it's there in the. I can just quickly check right now. Yeah, let's just quickly check on the thing. But yeah, does anyone else have any questions or? I'm just curious, like if people like also tried it out and have any sort of like, yeah, what their vibe of the model is.
Yeah, this model is very impressive, like vision wise. Like it's on par with GPT-4o mini or like sorry, I mean Cloud 3.5 Sonnet. I mean, I think this benchmark is a bit limited, so I'm sure from practical problems, Sonnet is better. But yeah, this is really strong despite being so small,
Yeah. Yeah, I don't know, maybe I'm not just finding it, but I'm not finding any mention of the image size. So I'm not entirely sure. Yeah. Yeah, I'm not sure. Anyway, I guess that's yeah, that's 5.3.5. I don't know if anyone else wants to add anything about it. But if not, let's see, is there any other question about 5.3.5 or any comments? Nope. Okay, so what is the next paper then we will cover? The next one is the yeah, sorry, go ahead.
Oh, I'm so sorry. Actually, I have to leave at 2 p.m. So could I possibly do the next paper?
Sure, yeah. So the next paper will be the JPEG-LM paper.
Yeah, it's a very like a short paper, I guess. So yeah, it's not gonna take a while. So yeah, they basically propose to directly model images and videos as a compressed files saved on computers via canonical codecs like JPEG or ABC. So they used default Llama architecture without any vision-specific modifications. So they pre-trained JPEG-LM from scratch to generate images autoregressively. So by directly outputting compressed filebytes in JPEG and ABC formats. So actually, this was more effective than pixel-based modeling and sophisticated vector quantization baselines. So actually, they achieved 31% reduction in FID, which is significant, obviously. So JPEG-LM has a special advantage over vector quantization models, in particular in generating long-tail visual elements like generating text in image, which is quite useful, I guess. So it's basically JPEG-LM, they first converted image into JPEG JPEG codes, and then they used BPE to produce BP tokens and sequence. So their BP vocabulary size is quite small, 320, and each 256 times 256 image was converted into 5K token sequence. So the compression rate is like 12 times. On the other hand, BQ baseline, they use vocab size of 4096 and sequence length of 1024. So the unconditional FID they measured was 155 for BQ and 121 for JPEG. So yeah, it's much better. And in particular, it outperforms stable diffusion on partial image conditioning. So yeah, that's about it. So the thing is that actually this image classification with JPEG code coded image was known to outperform image classification with low pixels. And the earliest paper I know was from like 2020 or so. So it's not, it's a very old method, maybe even before that. So, but I've never seen a paper that tried this on image generation. So this was interesting. Actually, outperforms VQ method, which is great. But unfortunately, they did not do ablation by changing the compression rate of VQ versus JPEG. So I think it's kind of hard to do that for JPEG. But so the thing is that if you adjust the compression rate of VQ, maybe the performance VQ would perform better. But they didn't do it, so I'm not super convinced. But the result was nevertheless very interesting. And also, entropy coding, the one used in JPEG, is often negatively affects language modeling performance on text. So yeah, this unfortunately doesn't work on language modeling. But yeah, on images and videos, it seems very effective. I want more follow-up papers on this. But obviously, there have been many interesting papers coming out on tokenization of images recently, especially there was a compressing an image into 32 tokens only with VQ vector quantization, and it performed even better than a lower compression rate. So yeah, I'm not super convinced by this result, but yeah, I just want to see more results. And do you guys have any question?
Yeah, I don't have any questions, but yeah, it's interesting. Yeah, I've also seen some of those papers on image classification and processing images directly in the sort of JPEG encoding. So this is definitely an interesting sort of work. And it'd be interesting also to I guess maybe the goal here eventually is to put this in multimodal models as well. So yeah, it'd be interesting to see if they do anything like that.
Okay, so yeah, I guess I can leave soon. Is there anyone else who can replace me? Maybe.
I think if Yam is interested, he can. Happy to have him join as speaker.
Yeah. Oh, we even have Lady. That's cool.
And did you want to also briefly cover the DeepSeek prover one, or?
Oh, I think I'm good.
Okay.
Yeah, sorry about that.
Okay. In that case, I'm happy to, of course, continue on by myself. But if if Yab wants to join, he can, or Riley wants to join. I'm happy to have him join as well. Cool. I guess Yam said he will join in a couple minutes. Okay, that works perfectly then. In that case, we will move on to the transfusion paper, and I'm actually pretty excited to talk about this paper. So I guess let me just put it up on the space, the link to the paper, and then we will get started. So this is a paper actually from Meta. Okay, so I've added it to the space. Okay, so the transfusion papers is this new paper from Meta that is trying to basically see if we can process discrete tokens and continuous vectors in the same model in order to be able to do things like regular language model stuff, autoregressive models on discrete tokens with the transformer, but at the same time also being able to do diffusion doing image generation and things like this. So yeah, basically you have a single model that's able to do both the language model generation and also diffusion. And so the idea is this sort of thing is basically it's comparing to, it's kind of it's different from the a previous approach, which is basically to do everything kind of autoregressively, including the image generation. So, for example, Chameleon, they had image tokens, and so those image tokens were, coming from like a VQ VAE, and you're generating the image tokens just like you would generate a text token, and it's like a discrete token that you're generating. And so that's how it was done in the past, where it was simple to have everything in one model where everything are discrete tokens. But here they're trying to mix both the discrete tokens with like continuous sort of data with the images and try to be able to generate the images. So that's the goal here of this paper. Basically, yeah, like I said, basically, yeah, you have text that's encoded with a pretty standard tokenizer. They're using like the Llama 2 tokenizer. Then for the images, they're actually using latent diffusion here. So there's actually a VAE that is encoding the image as latent patches. They did mention like the paper shows everything done with latent diffusion and with image latents, but they did preliminary experiments with pixel level stuff as well, and it does seem to work for that as well. So you could technically do it with pixel directly in the pixel space, but here of course they do it with latents, and so yeah, you're just like with the standard latent diffusion, you have your VAE. They train the VAE from scratch, so it's a new VAE altogether that they train on their data set. And then they get the latent patches. And yeah, so those latent patches are what's passed into the transformer. And then of course, like, just like with with very regular transformer, you have like your tokens, but then those tokens are converted into vectors and the vectors are what is processed by the transformer, right? So like with discrete tokens, like with regular language models, you have like an embedding layer that you get like an embedding for each token. So here you still of course have that for the language part, and then for the images, basically there's a separate sort of either they have like a linear layer or they use like a UNet down block in order to like give you sort of like an embedding for that particular patch. So you get some sort of vector embedding for that particular patch, and that's what's passed into the transformer. And then of course on the other side of the transformer, you typically have like an unembedding layer for your your text tokens, and then for your image, you again will, for the image patches, you have some sort of like again linear layer or UNet up block, and then that gives you finally the sort of image latents, which are then of course passed into your VAE to get the final image. And so yeah, but then of course the transformer is able to process those sorts of embedding vectors as as it normally does. Yeah, the other thing that's so that's like the typical, that's kind of the architecture. There are a few things that are important to note. For example, the attention mechanism and the attention mask of the model, which is very important. So, typically for transformers that are working on language models, you just have a causal attention mask, right? You have your current token, and the attention mechanism when you're processing the current token is only looking at the previous tokens, and that's you have an attention mask that that expresses that and allows that to happen. But for the images, basically you have the patches. It's kind of going left to right, to top to bottom kind of approach, and so it's done kind of sequentially in that sense, but it doesn't make sense to only have, you're looking at a current patch and it's only looking at the previous patches of the image. Like, you want to be able to look at the entire image when you're processing a single patch. So they have a bidirectional attention for the images. So it's not a causal attention like you would for regular language models, instead they have bidirectional attention. So yeah, that's shown in Figure 4 of the paper, where you have the sort of combination of the causal attention for the text tokens, and then the bidirectional mask for the image tokens. And then one interesting thing, which I saw on Twitter today, was that I don't know if you guys heard about the Flex Attention library developed at PyTorch, which is basically this library for implementing different sorts of variants of attention, and it's able to again be compiled and all these things. It's very highly efficient, and yeah, this is a library that was developed at PyTorch, and they said that this project was one of like the first projects outside of the development of the library that actually was using this library for like a research project and for a research purpose. So I thought that was kind of interesting. A sort of, and yeah, like it goes along very nicely. This is I guess like really great use case for that Flex Attention library. So I thought that was kind of pretty neat. Okay, what other things to note about this paper and how it works? The other thing that I forgot to mention was that yeah, you have the text tokens and the image tokens, but basically you have like a beginning of image token to tell the model, like, now we're doing diffusion, and then you have an end of image token once you're done with the generation of the image. So like, for example, doing inference, you do your regular sort of next token sampling, and then so you're sampling token by token, and then if you sample this beginning of image token, then you switch over to doing diffusion for the remaining tokens, and then once you're done doing your diffusion, you do regular diffusion sampling, then you add on an end of image token, and then you can continue then back to your regular LM mode of doing next token generation and sampling. So this is how you're able to do inference with both of these modalities. And similarly, then for trading, you have a language model objective, it's the standard objective there, which is applied to the text tokens, and then you have a diffusion model objective, which is applied to the image patches and the image tokens there. And of course, with the language model objective, that is computed per token, whereas the diffusion loss is computed over the entire image, which would span multiple image tokens or image patches. Okay, yeah, I mean, the architecture is pretty similar to Llama sort of architecture, Llama 2 architecture. Yeah, they train their own VAE. What else is there to note? Yeah, and then the data set that they're using, most of the experiments use a 0.5 trillion tokens with a ratio of 1-to-1 between image sort of tokens and text tokens. And the text tokens come from the Llama 2 corpus, and the image data comes from a licensed Shutterstock data set. And then, yeah, actually, you can mix, of course, these tokens, like the images and the text. And so you can actually do, like, for example, both image generation, but you can also do image captioning. So for example, you could do if you train with the caption first, and then the image tokens coming after that, and for that it could be for image generation, where you have the caption and then it generates the images. But then you can also do the opposite, where you have the image first and then you have the captions afterwards, and you can do that for like captioning, where you have the image and then that conditions the generation of the caption, the text tokens that correspond to the caption. So actually, they have a mix of that in the data set, but 80% of it is with the caption first for image generation, and the other 20% is for the image first, so that you can do image captioning. And then, of course, they train models at different scales, 0.16b, 0.37b, 0.76b, 1.4b, and 7b parameters. And yeah, okay, so now let's go on to the experiments of the paper. And so the first main question that they want to address basically was, is this better than the chameleon approach, which was basically just treat the images also as discrete tokens, because you can use like a VQ-VAE to do that, and then you can just do like standard autoregressive loss. And like obviously, like yeah, I mean in some sense that is a bit simpler. So the question is this really any better than the chameleon approach? So they basically trained both their transfusion models and also chameleon models at different model sizes and token counts, in order to basically put together scaling curves for the for transfusion and chameleon models. And they noticed that basically the transfusion consistently exhibited better scaling laws than chameleon. The scaling lines were close to parallel, but there was a gap in the favor of transfusion. So like just generally, like even though they scale similarly, transfusion overall is like better most of the time than, or yeah, it was always better than chameleon at all the different scales that they tested. And yeah, the other thing that they found interesting was that even text, of course, they did the evaluation for like image generation, where they got like better FID with the transfusion model compared to the chameleon model, and getting the same FID as chameleon with 34x less compute. So there's a lot of benefit again, like with the scaling of transfusion over chameleon. But like, okay, that's with the image generation. But what they find interesting is even the text-only benchmarks were better with transfusion, even though it's still going to be the same sort of modeling. It's still next token prediction for transfusion and chameleon. So they were wondering, why is it the case that transfusion is better at text-only benchmarks when it's modeling the text in the same way as chameleon? So yeah, they what they notice is like the chameleon training is a bit like unstable, and like the chameleon training has some stability modifications to the architecture. So the architecture is not exactly the same, even like the sort of the transformer architecture is not exactly the same compared to transfusion, because they needed these sorts of modifications to the chameleon architecture in order to stably train the model. And then on top of that, like you also have these sorts of image tokens, and their hypothesis is that there is maybe a competition of generating image tokens versus the text tokens, and then or also like maybe diffusion is more efficient at generating images, and so therefore requires fewer parameters, and so that the transfusion can use more of the model capacity, more of the parameters to focus on generating text compared to chameleon. But they say that this of course needs to be analyzed more carefully in a subsequent paper or subsequent work. So, but that's a very interesting sort of observation that they had. Okay, and then of course they did a whole bunch of ablations, which of course they found, for example, the bidirectional attention gets better performance than causal attention on the images. So yeah, I mean it makes sense. Of course, you would want bidirectional on the images, and they did an experiment to show that it does improve. I mentioned the sort of like embedding layer that they have for the images, where they could do a simple linear versus having UNet up and down blocks. And what they noticed is that the UNet up and down blocks perform better than the linear. And they said they say it's because of the inductive biases of the UNet architecture. They said that an alternative hypothesis could be that there's just more parameters when you're using UNet layers. So in order to study that, they actually just kept scaling up the transformer model without changing the number of UNet parameters. And they say that as you increase the transformer itself, the benefit of the UNet layers shrinks, but it is not diminished. So they still think that there are actually some inductive bias effects, that using a UNet is better than using a standard linear layer. Okay, and then finally, of course, like this was comparing to chameleon, like most of their stuff was comparing to chameleon and ablations. If you compare to actual like state-of-the-art models in the field for like image generation, for example, they observe similar performance to Deep Floyd. They say it surpasses SDXL. Of course, they don't beat SD3, but they're saying SD3 uses synthetic captions, whereas this model was only using natural captions. So they're saying maybe there's still a way to further improve this model, and it could maybe, I guess they're hoping it could eventually pass SD3. Yeah, that's that. They did this on the Gen Eval benchmark, which is one of the more common recent benchmarks that people have been using. And then a very interesting, interesting thing about this paper was that, using this as like a base model and then adding additional capabilities. So for example, they tried to add an editing capability to the model. So basically they fine-tuned their 7B model on a data set of 8,000 publicly available image editing examples. You start out with the input image. So you have the input image tokens or input image embeddings. Then you have a prompt corresponding to the edit, and then you have an output image that you want to generate. And then you could, so like they do examples of like, remove the cupcake from the image or something like this. And they didn't do any quantitative evaluation of this, but like qualitatively, that the results that they show look pretty good. So that's kind of impressive that this model can also do these other tasks. If you just fine tune it with very little amount of data, they have only 8,000 examples that they were fine tuning with. So yeah, that is the transfusion paper. I think it's a very exciting project. And yeah, like I think people kept thinking. I think a lot of the sort of consensus so far had been like, if you wanted to do like truly multimodal models that can take in different modalities and output different modalities, the best approach was to do everything autoregressively. And that was just going to be the easiest approach. But here, they're showing that maybe that's not necessarily the best approach, and that actually using diffusion could actually be helpful in this case, and incorporating diffusion as part of their sort of truly multimodal sort of model. But of course, I think there's still some limitations. I think, they still have, limited scale and limited data sets. So of course, you just want to, there's some work, of course, to scale it up. There are other sort of extensions that you could do. For example, all of this was done with like diffusion, but of course you can extend this to flow matching, which is what all the latest image generation approaches use now. And then also, I think one thing to note is like, they have the image captioning stuff and they show good results for that. But it's not like a true like sort of interleaved sort of sort of interface with the model or things like this. So I think there's still like more sort of like vision language sort of multimodal capabilities that haven't really been studied with this model and that need to be studied further. Like just basically like image understanding and things like this. They hadn't really studied that very carefully with this. And so it's unclear if this model actually has any good capabilities for that, or if it's possible to train those capabilities into the model. So that's another aspect. But yeah, apart from that, I think it's certainly a very promising direction. Yam, did you have any thoughts on this paper, Yam?
I think the whole approach, it's crazy that you can just build whatever you want into the context and add the diffusion losses and things just work. I don't know, it's just the magic of deep learning that everything just works. And it even, like you said before, it even somehow, I'm not sure exactly by which loss, but something forced the embeddings of the image and the text to be fused together to the point that it improved the text. Which loss even did that? It's so crazy. I mean, it's an amazing paper. It's an amazing idea. Absolutely. It's just crazy that it works at the end. And works, and they prove that it works better. Like it does something. It's really crazy. And at the end, I think that multimodal in, multimodal out is at the end will be the future of all of these type of models. But it's really crazy that it just was that kind of simple. You just need to have this idea, and deep learning, it just works at the end. But yeah, it's an amazing paper. I didn't see it coming. There are so many papers this week.
Yeah, again, coming from the Meta group, I'm really impressed by the research that's coming out of Meta recently. So pretty excited by that, and we'll see if they extend it further. I really hope they do. It'd be interesting if they can extend it to other llama models. that's another thing. Maybe it'd be interesting to explore is like fine-tuning llama models in order to be able to do this. That could also be another interesting research direction.
You know what I
Yeah, I
think,
mean, there's
Omar?
just so many ideas that could be explored.
There is something that is surprising, that you're using the same attention weights, sometimes with causal masking, and sometimes with actually. When I'm saying this now, actually, prefix LM is exactly the same, and it works really well. So yeah, you can use the same the same attention weights, half of them with causal masking and half of them fully connected. I just thought it was weird for a sec, but yeah, you're fusing all the emetics, but it makes sense. There are other models to do this successfully at the end. So yeah, really cool. It's really cool.
Yeah. Yeah. Does anyone else have any thoughts? I don't see any sort of comments or questions about it. If not, yeah, I'll move on to the next paper. But yeah, really excited by this paper, and hopefully we will see lots of future work extending this. Okay, so the next paper that I want to cover, and I guess would be our final paper for the day. It's the to code or not to code. Let me pin it to the space. So this paper is coming from Cohere, and they are exploring the very important question of if incorporating code data in your pre-training data set improves the general performance of the model.
This is conspiracy theory levels. And this question is going 3 years. It's like a conspiracy theory. Everyone thought that it might be the secret. And finally we get a confirmation, a conspiracy confirmed. Yes, it does improve the model somehow.
But
only if you do it in the right percentage, not too much, but yeah.
Yes. Yeah, I remember everyone was talking, like, especially like, then GPT, like the Chat GPT and, GPT 3.5 and even GPT 4, like everyone was talking about, oh, this must be one of the secret things that OpenAI is doing. I remember that was a huge discussion at the time. And I mean, there have been several even open source models that incorporate it in the data set. Like, if you read the paper, they actually mention, like even like the llama model is included, and there were some other papers that have analyzed this question kind of for limited topics. So for example, like there was a paper that analyzes it for mathematical reasoning or like certain specific capabilities, but they wanted to kind of study this more broadly to see, just generally if using incorporating code in the pre-training helps. And they analyze a few things here. So they analyze things like, training from scratch, pre-training from scratch, and if the code is in the data set for that, or initializing a model that was trained with code and then continuing the pre-training of that. Another aspect that they look at is cooldown of the model. So like oftentimes, when you're when you're wrapping up your model training, your model pre-training, you will decrease the loading rate and switch to a higher quality data set and train that for like the final stages of training. So that's referred to sometimes as cooldown. And so a lot of the state-of-the-art models these days do this sort of thing. And so they also was asking like if you include code in that phase of the pre-training, if it helps. So they're trying to analyze all these different questions. The data set that they used the Slim Pajama data set. So that's their text data set. Of course, that also includes a lot of code and all kinds of other stuff. So they do filter all of that out because they want to, make sure that it's not a confounding factor there. Slim Pajama usually has a total of 627 billion tokens, but removing all the code related stuff, they end up with 503 billion tokens. And then on top of that, of course, they have their code data set. So they're mainly using the stack data set. And that's like one of the sort of common open source code data sets now, which it was the data set that was used to train the StarCoder models. and it's basically data coming from like GitHub and things like this. And they have about 139 billion tokens for that. But they also like do other sorts of things like they try to incorporate markdown tokens and markdown CSS HTML. They also try to incorporate synthetic code. They do not talk about where the synthetic code dataset comes from. They just say it's a proprietary synthetically generated code dataset. So I don't know anything about the details about that. And of course, they include things like, they also include things like GitHub commits, Jupyter notebooks, other sort of like code adjacent data is what they call it. But yeah, those are the datasets that they analyze with. And then they try to evaluate the model across a few different axes. So they have like world knowledge, natural language reasoning, and of course they want to just still check like code performance if that improves, which it of course should. So there's kind of like a sort of like a sanity check in some way. And then also they
really strange. Like why? Like why it helps? Because of the repetition? Because you need to close the brackets so the attention, I don't know, pay attention to where they open and where they. It's just why. There are so many things that are related to data quality or specific type of data that somehow by magic improve models, and we just don't know why. We found out it works, but it's pretty crazy that code improves other things that are, I don't know, completely unrelated at the end.
Yeah, and I'll get to that a little bit more because it's these results are a little bit, even in this paper, some of the results are very kind of counterintuitive. And I feel like maybe we need more studies just to even kind of replicate this or like kind of confirm these results because some of these results are pretty counterintuitive. Anyway, talking about they look at world knowledge, natural language reasoning, regular text generation, which they use like an LLM judge kind of evaluation. And then the other thing, I guess, which I will say is kind of maybe a limitation of this paper, is that they only look at models from size 470 million to 2.8 billion. So these are some pretty small models that they're looking at. So it's unclear if whatever trends that they observe in this paper will scale up to larger models. And I think, we'll have to see a more comprehensive study at larger models to actually analyze this. So let's going through the results. The first sort of experiment that they were looking at is basically initializing an LLM with code pre-trained models. So for example, like I remember like there was some discussion with ChatGPT and GPT 3.5 that these sorts of models were initialized with Codecs, which was like OpenAI's code model. I don't know if people even remember Codecs these days. I remember that was a big hypothesis that everyone was talking about. Exactly. Yeah. So, people were saying, initializing with a code pre-trained model, and then training that on general text would help.
Yeah, I think it was a mistake in the documentation that just threw everyone to somewhere completely unrelated. I mean, look, code at the end, code improves models, and we saw it in small experiments. But I think everyone started to get this idea by some sort of a mistake in the documentation, because I don't think that it was trained from Codecs. It makes no sense. I really think that it was just a typo in the. It's a long time ago, but I think it was just a typo. But anyway, I mean, look, people were debating this question for so long, so it's really great to see such an extensive study for what exactly, which type of code improves by how much, and so on and so forth. And we talked about Phi. Phi has their own tricks related to data, which probably are somewhat similar to directly selecting things that improve models in terms of data-wise that we just don't know. But so it's really interesting to see and find out those type of phenomena that somehow improves models, because it's extremely unintuitive at the end. So it's pretty cool.
So just quickly going through the results here. So like with initializing on code pre-trained models, they say if you that improves reasoning, but also improves. So this is what I guess was it saying? Initializing on 100% code gives same performance as text-only baseline, and initializing on 50% code gives a 4.2% relative improved gain. And this is for knowledge tasks. So this is what I find very interesting, because why would you expect improvement in knowledge when you're trading on code? Like it's a that I find very counterintuitive.
There was a paper about taking the pile and removing each one of the sub data set inside of it and training a model and see how it influenced. And at the end, all the experiments turned out extremely unintuitive. Like you remove Wikipedia and the model gets better at factuality, things that makes no sense at all.
Yeah.
At the end of the paper, the one conclusion that was obvious throughout the whole paper is that the diversity is one of the things that extremely improve everything. So this might be the case here, that if you have a diverse data set with both code and text, it improves everything just because of the diversity, because overfitting and repeated patterns and so on. If you have more of them, maybe this is what we see here.
Yeah, so that was the only thing that I found. Yeah, I found that like a very counterintuitive result, that initializing on model that was trained on code would help or like gives even similar performance as like just a regular text model. But that's it could be. I think I guess maybe that should be like looked into further. But yeah, it's possible that the diversity it's just a matter of because of diversity. And then, of course, they do scaling experiments where they show, like, they did this at 470 million up to 2.8 billion, and the trends are basically the same at all these different, scales. So, I'm not going to go too much into that, except, the trends are the same. And then so that was like initializing on a code model. But then they talk about, like, okay, if you're trading from scratch, if you include code as part of the pre-trained data set, what are the results? And again, they observe like there is like having some code does improve reasoning and world knowledge. But then this makes more sense is that, of course, if you increase it too much, you'll get a drop in performance. So like if you like they say the average performance starts to decay at 75% code in the data set. So like if like 75% of your data set is code, then it's not going to be able to learn other you don't have like much knowledge in the data set, or like that makes sense. But then also they said not including code at all hurts the natural language reasoning performance. So they're saying like I guess that it is important to have some code to, at least for the reasoning, you need to have the code in there to get the best performance.
Just question. They have an experiment where it's not code but a different thing that is not text, just to to rule out diversity. Because if you take something else completely, I don't know, a new language, for example, I'm not sure, and it does work. So it's not the code, it's the diversity. However, if it doesn't, well, it's the code. So I'm just saying maybe they had something, because they had a lot of ablation studies.
Yeah, I'm not sure if they did that. Let's see. I think there was discussion of I actually don't think I don't remember seeing anything like that specifically. That is a good question if they could be a worthwhile experiment to do. But I don't remember coming across that sort of experiment, and I'm looking at the paper right now. I don't think I see anything like this in either. Like for example, I don't know. I mean, I would expect a lot of these conclusions would also be similar with like just multilingual. I don't know. That's like if multilingual trading also would show similar sort of thing. But like that, I guess multilingual wouldn't help for things like reasoning and stuff like that. I think that's the big thing. Is like with code is the idea that it helps with reasoning specifically, and like there's some interesting properties about code that enable that I guess it can, like, because it's like a lot of code is like a sort of step by step. I think someone was mentioning this. David was saying, he mentioned, my theory is that code is similar to chain of thought. Moreover, code is probably correct, so there are like validated chain of thought trajectories, basically distill logic and reasoning. And yeah, I think that sort of makes sense to me as well. And so it would be hard to kind of parse that out. And I don't know what other sort of like non-code data with that would have a similar effect would be. I don't know. But yeah, I think that's a good question though. Yeah, let's see. So anyway, they incorporate, yeah, so as I mentioned, so they also, basically including code is important for the reasoning stuff, and then also improving, utilizing high quality synthetic code data also gives a benefit for continual pre-training, or like incorporating the pre-training data set. So, again, I assume this is like, again, things like, for example, Phi is doing, they're incorporating synthetic code data, and or even things like, yeah, eval instruct. I guess maybe the Hermes 3 people, they're probably doing something like this too, maybe. And so that all helps with reasoning. And then also incorporating code in the cooldown also it helps with improving reasoning. But yeah, I guess they yeah, what is it here? Sorry, I think the cooldown stuff is a little bit including code in the cooldown phase where high quality data sources uploaded provides significant improvement on natural language reasoning, world knowledge, and of course code performance compared to without cooldown. Yeah, so overall, I think it's kind of, the conclusion is basically incorporating code in all these different places helps. Of course, incorporating too much code can harm the model as well. So there's, of course, a necessary balance. But I think, I don't know, because Yam, I think, of course, you spend a lot of time, training and evaluating these sorts of models. What do you think of these sorts of benchmarks that they did choose to analyze here? Are these good benchmarks? Because my understanding was these benchmarks are fairly limited. So, for example, for world knowledge, they're looking at trivia, QA, natural questions, open. Those are the world knowledge benchmarks. For natural language reasoning, this includes things like Bool Q, Superglue, HelloSwag, Vinogrand. Like, my understanding is that these are all pretty outdated and kind of, not the
I'm
best.
not sure why not MMLU,
Mm-hmm,
at least.
yeah.
Yeah, I mean, look, I think the effect is there, but yeah, it would have been easier to know just how significant is it, because if there was, I don't know, for factuality, for example, there was MMLU. Let's see what they measured for code. Okay, I see. They took like a suite of benchmarks, and then they divided them into groups for reasoning code, and for reasoning, world knowledge, and code. And then they measure like an average. I think an average for each of the groups. Each of the groups, just so they
that was my understanding too.
Get a wide view of how good the model is on many different benchmarks.
Right.
And I can understand that. Look, they want to know if in general it improves reasoning and not a specific type of data set, which if you're changing the data of the model, you can easily overfit stuff if you play with it too much. So yeah, I mean, it would have been nice to have more benchmarks, but I think the effect, I think it's pretty significant, the results. I think it speaks for itself. Yeah.
Yeah, I guess my biggest concern was basically these two things, was whether or not these are useful benchmarks in the first place, and also whether or not like these are going to transfer to larger scales, because it is pretty, the results are done at a pretty small scale, both in terms of, especially the models are 2.8 billion is very small. So those are my two questions. I think, of course, future work will hopefully look into this further, but So yeah, those are my
it's an
two questions
important
and
question.
caveats. But apart from that, I think at least it's a good study in the right direction. And I think we're like starting to see more like confirmation of this. Like I feel like it hadn't been studied very carefully before, and it was just kind of like anecdotally like just like, oh, everyone is saying code is better, and people were just starting to try to use it for things. But like like when I remember asking people if there was like any like one study to point to kind of show that code is good for these sorts of things, and people didn't really have like one study to point to before, and they were like, oh, in this paper there are like a few results here, and that paper there's some few results, and like they're like not people couldn't really tell me like if there's like a comprehensive analysis before of like how much code is good and things like this. And this paper is starting to get there. Of course, it's still like not perfect by any means, but it is certainly starting to get there. And like I think it's I'm hoping that there's still there'll continue to be more comprehensive research like this in studying this question.
Yeah, I think the whole dataset mixture and what to include or not include in the dataset is extremely important, and we are kind of guessing it now. Apart from educational value, which is something that we know, I don't think we know a lot at the moment. So any study that checks the different influence of different type of data sets in the training is very important. So absolutely,
yeah. Someone was just saying, would be curious to see Mistral's take on code training data because theirs may be bilingual comments. Yeah, I mean, I guess Mistral is their probably data set is bilingual, but they probably will still see a benefit from using code data. Like again, like I was thinking like maybe multilinguality will show some benefit, but like it's still not going to include the sort of. I don't think it will include much of the reasoning benefit. Like the whole point with code is like it's going to provide the sort of reasoning. I think the question of like code versus multilinguality will maybe help. Yeah, will help parse together the difference between if it's just a factor of diversity or if there's something else special about code. I think that's
I found when training multilingual models that certain languages improve certain languages, like different languages,
okay.
but certain languages do not. What I don't know, it needs to be studied, but just from my initial experiments, what I saw is that languages that are extremely different than English, things that are completely non-English, like Arabic and so on, improve the model a lot on many different languages. And I think it has to do something with data diversity, because you are adding an extremely diverse type of distribution into the data. I think, I don't know. And
right.
So yeah, it was interesting to see that some languages improve, different languages, some languages do not improve. It's crazy when you think about it, but at the end, it might be something like the diversity of the data, and then it makes sense. It's not that crazy. But yeah, it needs to be studied. It's an open question, a very interesting one.
Yeah. So that would be interesting to study if it's just a diversity question, part of it's just diversity, or if there's other sort of special properties that code has. And I think comparing multilinguality with code, that could be interesting to study. And like what multilingual models are able to achieve, or like parsing that out. There's so many different also confounding factors. So but it's certainly a very hard question to study, but it's a very interesting topic. And at the end of the day, also it's just like half the time it's just the models like just do things that we cannot understand what's going on. I don't know. It's like there's also just some of that as well. Like I don't know. It's just like all kinds of very weird and counterintuitive effects happen, and like just like you were mentioning with the transfusion paper, like all these things. It's like just learn things and we don't know how and why. It's like very you just gotta try things out.
The transfusion paper, I can understand why. I can understand like the intuition because of why it will work. But here is, I don't know, a data set mixture is completely like black hole. It is everything is counterintuitive. I'm surprised that we got to the point where we have such a clear, simple law of educational value that seems to be always working, because this is, I think, the only thing we're going to find that is going to be that easy. Everything else is going to be extremely hard to find, because I don't know, it's just hard, the whole thing. But even that, I can speak about this for hours. It's crazy that it works on its own. It can be, this type of educational value can filter so many different things that are not educational value by mistake, and we just think that this is what we're doing, but I don't know. It's just, you know, those things are crazy as they are.
Yeah.
So,
cool.
Let's see. Yeah. Mm-hmm.
Yeah. You have anything else to add about this paper?
I'm happy that we finally got an answer.
Yeah.
To this question. Finally.
Yeah. Cool. In that case, yeah, I don't have anything else to add. I don't think I see any other questions here. So yeah, I think with that we will end the space. And yeah, this is a very good space. We had it's great that we had the Hermes people, Mozilla talk about that. That was a really good discussion. Talk about the transfusion paper, this code paper. So lots of interesting discussions today. So thank you everyone for joining. As usual, we'll put up the recording shortly. The recording's there on the space, of course, but then also on like as a podcast as well. So that will be up shortly as well. But yeah, thank you everyone for joining, and please join us next week as well. And I hope you had a good time, everyone. Talk to you guys later. Bye.